Hi everyone. Today is one of our new IYCN Science Café, together with Professor Erwin Reisner, who are gonna give us a presentation about his latest research on liquid solar fuels. So a brief introduction about me. My name is Wade Hiba. I'm the IYCN IYCN Conference President's Committee co-chair, together with Tracy Rowe. Tracy, can you introduce yourself?
Hi everyone, thank you for joining us. My name is Tracy Lau and I am IYCN Conference President's Committee co-chair with Walid as well. I am also joined with, would you mind introducing yourself as well?
Thank you, Tracy. My name is Elisa. I am currently a PhD student at the University of Coimbra, Portugal, and I'm a member of the International Younger Chemists Network. I'm very glad to co-organize this event, and I want to take this opportunity to thank Professor Reisner for accepting the invitation and the audience for joining us today.
Okay, so proceeding, we will have like 5 minutes an introduction about Professor Erwin Reisner and the IYCN, and then followed by a brief presentation by Professor Erwin, about 30 minutes. Then we will have a Q&A session and then closing remarks. So beginning with our organization, the International Younger Chemists Network is an international organization associated with the IUPAC since 2017. Our vision is to connect and empower younger chemists globally, and our mission is to support and advocate these scientists across chemical sciences towards a globally sustainable future. So if anyone is interested in joining our community and our network, you can from this link, the IYCN global.com/membership. You can apply. Our membership is for free, and we have multiple committees. You can look it up and see it. Also, if you want to connect with us, you can you can either email us or you can connect with us on several social media platforms, from LinkedIn to Facebook to Twitter and Instagram. Finally, this is a picture of our delegates attending the first IYCN Chemical Assembly in Paris, and soon we'll have a second General Assembly next month. So we are waiting all for you to attend and network with each other. So going ahead, so our presenter, I would like to thank Professor Erwin. Professor Erwin Reisner from University of Cambridge received his education and a professional degree from the University of Vienna, PhD in 2015, and then he went to Massachusetts Institute of Technology, MIT, as a postdoc from 2005 to 2007, and then the University of Oxford as a postdoc from 2008 to 2009. He has recently received an award from the ERC Advanced Grant in the work of biological domino catalysis for solar chemical production. He's also currently acting as the academic lead of the UK Solar Fuel Network, currently as a co-director of the Center for Doctor Training in Functional Nano in Cambridge, as well as a member of the European Research Consortia, Sofia, and Solar to Chem. So without further ado, Professor Erwin, the floor is yours.
Excellent. Thanks a lot for the very kind introduction, and thanks to Tracy, Elisa, and Walid for hosting me. It's a real pleasure to be here and talk to the International Younger Chemists Network. And let me share my slides.
Yeah, you're now as a presenter.
So the title of my talk is Liquid Solar Fuel Synthesis. And I have to admit, I'm really impressed by the Younger Chemists Network, because it's the first time in my career that I was actually told what the title of my talk was supposed to be. And I, of course, adhere to the introduction and will talk about solar fuels, our approach to build devices, in fact, that make sustainable chemicals, and then at the end really focus on liquid products, which we have achieved recently. So I would spend the first maybe third of my talk on a more broader introduction, hopefully to convey the message to the younger chemists as well in the audience that this is quite an attractive field which holds a lot of promise, I think, for the future. So you will all be familiar with solar panels. Solar panels are, of course, being rolled out at a large scale, luckily, and they produce electricity. And that's, of course, very good but there are also certain limitations. If we look at the global power demand, and here on the right there are numbers roughly from 2023, you will see that global electricity demand is only about 20 or maybe 25% of the global total. So this means there's still a massive need for fuels and chemicals, and which of course makes then up the other 75 or 80%, and that's something we'd like to address. So the idea is more or less, can we produce some sort of device that resembles a solar panel that does not only generate electricity, but actually can make fuels and chemicals on demand to exactly address this gap in sustainable energy generation we have at the moment. And the case for solar energy today is a very strong one, and this has changed dramatically in the last 15 years. So what I'd like to show here is a plot of the cost of electricity that's expressed as levelized cost of energy in US dollars per megawatt hour. And this is the cost of electricity if you were to build a new power plant today and let it run until the end of the lifetime, and how much it would cost to produce the electricity. And then I only give 2 time points. One is 2009 and 10 years later in 2019. If we look at coal, gas as a fossil powered electricity and nuclear, you will see that the prices did not change dramatically. Nuclear went up a little bit. This is mainly due to maybe smaller scale implementation of nuclear and also more stringent safety considerations, and coal and gas went down a little bit. I know this is 2019 and not 2023. Wind was very successful. So in this case, wind from $135 per megawatt hour today is far cheaper and hovers around 2019, $40 per megawatt hour. But most remarkable was photovoltaics. So in 2009, photovoltaics were of course already known and produced at significant scale, but they were quite heavily subsidized because they were not really economically competitive in most places with other electricity generation sources. But within 10 years, the cost came really down very significantly. And it is now in many places on Earth the cheapest form of electricity, and this ultimately also translates into energy. So my case here is, if you can use photovoltaics to absorb light, to generate electron hole pairs or charge carriers, you can use them to make electricity or ultimately drive chemistry. And that's what we hope to do. And of course, you may know that the last 4 years were a bit turbulent when it comes to energy prices. This means in this 4 years, the fossil energy went up very significantly at certain times, whereas in principle, the renewable should go further down as scale out still expands globally. So what's the case for solar energy? It's already abundant and cheap, one of the most cheapest forms we have. The learning rate of solar energy is about 20%. This means if we double capacity, the prices come down by 20%. So it should actually become cheaper and cheaper. But at some point, we will saturate the electricity market, and then it will become very relevant that we learn to store energy and ultimately produce green fuels and chemicals, because we also have to transition our petrochemical industry into a sustainable industry to meet our 2050 targets. So that's my reason for solar energy, and I think today it is really an economic case. It just makes sense to do this. Why should we bother about chemistry? And I like this plot here quite a lot. This comes from a quite recent policy report that was co-authored by 2 of my former PhD students, Jen Leung and Andreas Wagner. And what this shows here is different sectors and their transition from a fossil-driven sector towards a fossil-free energy sector. So the plot starts on the left by 1991, sorry, that's a bit small, and ends on the right with 2050. And you will see that different sectors have different shadings, and the shadings really indicate where we are in the transition here towards a sustainable sector. And these little dots here show the tipping points. So if we take electricity, for example, renewable electricity in the early 2000s was quite a niche market, and we are already beyond the tipping point, and we are really in mass market. In many parts of the world, certainly developed countries, we have a lot of renewable electricity in the form of wind, solar, hydroelectric, etc. So this is really moving into late market already. And you can see that these sectors are now very different. So if we go to light road transport, you will see 2023, we are roughly at tipping point. And what does this mean? This is the transition really from gasoline or diesel powered cars to electric vehicles. And as you will know, 10 years ago, it was in many parts of the world quite rare to see an electric vehicle. Today, we are all used to it. And this is reflected here by this graph again. We are going really from a niche market, in this case, to mass market at the moment. But where are we in the chemical energy sector? As you can see here towards the bottom, there's this whole listing of aviation, shipping, so really heavy duty transport, then steel cement manufacturing, and really chemical production. And you can really see that these dots are quite far into the future. Of course, depends on which sector, and the chemical sector is huge as well. So one dot does not do this justice, but long story short, these tipping points lie about 10 years or sometimes even more in the future. And I think that's an enormous opportunity for chemistry, because this means it's really up to us now to develop new innovations and technologies that can really drive this transition towards a sustainable sector. And it's also, I think, a very strong case for academia, because we are still very early stage in this transition. There's still enough time to implement really new technologies. So if you find something in your academic laboratories, in your master thesis or PhD, you have time in a couple of years in this niche market, once you go from solution development into niche, to really potentially implement such technologies. And I think this makes a huge difference being here a chemist today versus maybe working on electric vehicles or renewable electricity, because you're dealing now with very mature markets. So if you find a better solar cell, you really have to find a very good justification why this can compete with a silicon PV or other technologies. So I think that's very unique, and it's probably a fantastic time today to be a chemist. And this is exactly what a lot of students in my group are exploring as well. So if I go back 10 years ago, we were a very academic lab. But as we develop more early stage technologies, also the students become more entrepreneurial. I only give one example, Sarah Lemeson and David Wakerley. They were both postgraduate students in my group, and they run now a very successful startup company, Diocycle here. And what they're doing, they develop electrolyzers for CO2 conversion. So of course, the sustainable chemistry space does not only apply to solar technologies, it is really a very broad space where I think you can make a contribution, and where your skill set is ideally suited to enter and hopefully do something good for society. So what's the vision and the mission of my laboratory? How do we approach this? We really work on a circular economy. This means we think quite carefully what kind of sustainable resources we use for our chemistry. First of all, water is the ideal liquid, the ideal solvent, and probably the ideal source of hydrogen and possibly oxygen. So we work a lot with water, in water. This includes polluted sources such as seawater or wastewater. We also look at components in air. Of course, carbon dioxide is a very important one. It's abundant everywhere, unfortunately extremely dilute, or luckily extremely dilute. We don't want to have it more concentrated, but it's very difficult to grasp, of course. But if you can take the greenhouse gas carbon dioxide to do chemistry, this would be a real advantage. That's something we are tackling. The same is true for nitrogen. Nitrogen is much more concentrated in air, so if we can do some chemistry with nitrogen, that's very attractive. And with CO2 and nitrogen, we can add two more elements to our chemistry toolbox, carbon and nitrogen. And with hydrogen, oxygen, carbon, nitrogen, you can really make most of organic molecules, which means energy carriers and platform chemicals for the industry. And last but not least, we had in the last 5-6 years a very quickly growing interest in waste conversion. So what about biomass and plastic waste? I think you're all aware of plastic pollution. So we look at plastic waste mitigation and actually using plastic as a resource to do chemistry. And we are also interested in biomass waste, specifically lignocellulosic biomass, because we do not compete with farming in this case. So this is a non-edible form of biomass. And last but not least, also some of our technologies we want to explore in organic chemistry to already help transitioning the organic sector as well to become a more sustainable part of the world economy. Just to show you, we are quite serious with this. One picture, this was taken last year. In fact, this was the first excursion we did after all the lockdowns. That's me with a couple of my team members. That's when we went to the Cambridge waste recycling facilities, really to source some real world plastic waste. and actually explore how we could implement our technology in such a waste scenario. But today I will not be talking about waste at all, but I just wanted to make you aware that I think this is also an extremely interesting direction of research. So what do we do with all of these sustainable resources? Well, we need to convert it into something more useful. And in our case, we use really solar-powered chemistry, so chemistry driven by sunlight. And this is our energy input, and this means we can actually generate quite high energy and interesting feedstock chemicals. Hydrogen from water would be one obvious one for a hydrogen economy. Sourcing ammonia from nitrogen is very attractive. Maybe there's a possibility to replace Haber-Bosch process. And last but not least, the large organic chemistry or carbon chemistry. We see one building blocks like carbon monoxide and formic acid, or C2+, so multi-carbon products like acetate, ethanol, and propanol. Today, I will really focus specifically on the conversion of carbon dioxide to products. And as the invitation was on liquid fuels, I will talk at the end a little bit on how we make ethanol and propanol with a solar reactor. And then, of course, with these feedstocks, since they're high in energy and you have all the chemical composition you need, you can in principle derive a very large range of different chemicals. So, for example, could we make green forms of gasoline or kerosene? This would be interesting, of course, to make aviation sustainable, for example. Can we make green fertilizers and support agriculture? And then also, can we really transition the petrochemical industry and make it green? Can we make sustainable plastics, pharma products, materials, and so forth? And of course, with these final outputs, what we want to do is reuse them as much as we can, recycle them mechanically if possible, and in worst case scenario, if even chemical recycling is not possible and we really combust it or throw it out, we are just back where we started. And this is really, again, the concept of a circular economy, which we hope to support the development here. Okay, but let's go into some of the systems we are exploring. And again, this goes to the idea of solar panels for chemical synthesis. So instead of having a photovoltaic module on your rooftop, what about just putting this into an aqueous reactor where you have your substrates, for example, carbon dioxide or also waste, you shine light and actually you do your chemistry. That's kind of a very simple concept I would like to present today. This is actually quite a niche activity in the global field. Usually most researchers work on photoelectrochemical cells where you have two electrodes that are powered by light, or suspension systems where you have semiconductor powders, or something a combination of a photovoltaic with an electrolyzer. But in this case, I find this quite attractive because everything is integrated, and I think it's a good illustration of what this chemistry can do. So if you do this all integrated into a single panel, you actually have two possibilities of configurations. First, it's known as the leaf configuration, where you essentially have all your light absorbers and catalysts as layers, or you have sheets where you have your light absorbers and catalysts co-deposited as powders on a substrate. I will not talk about sheets at all. I will only talk about this leaf configuration here, and again focus on CO2 to fuel conversion. This idea has been around for quite a long time in the community, at least since the end of the last century. But the first real practical demonstration of an integrated device was only in 2011, where it was shown that you could just take a triple junction silicon solar cell, sandwich it between two catalysts. In this case, there was a water oxidation cobalt phosphate catalyst and a nickel molybdenum zinc proton reduction catalyst. And when you shine light, the silicon creates a photovoltage, and we have effectively connected these catalysts that are powered by the voltage, and they split water into hydrogen and oxygen. And this was termed as the artificial leaf. At that time, there was a lot of activity. In fact, there was a lot of interest in this technology, but ultimately it was abandoned for commercial application because the case was that the hydrogen production using this technology, even in the most optimistic scenarios, was actually more expensive than really targets by the Department of Energy in the US. So it was just a bit too expensive as a technology to do it this way. But we actually got inspired by this configuration and thought, if hydrogen is too cheap, can we make something of more value? And this brought us into carbon dioxide conversion, making organic products, upcycling waste to chemicals, with the hope that higher value creation could make this actually a commercially relevant technology. So this was easier said than done. We started in 2012 a 7-year laboratory here in Cambridge with the single objective to develop a solar-powered reactor that could take now carbon dioxide into syngas. And syngas is a gas mixture of carbon monoxide and hydrogen. And in this reaction, you always co-produce some oxygen. So because the CO2 reduction here to CO and water reduction to hydrogen requires electrons, you source the electrons from the oxidation of water to generate oxygen. And we were very interested in this approach because with syngas, you can actually do a lot of chemistry already with established routes. For example, you can make liquid fuels. You can use syngas with Fischer-Tropsch chemistry to make hydrocarbons. You can make platform chemicals like methanol. You can make plastics, and you can even use the hydrogen to make the fertilizer production and steel manufacturing more sustainable. And syngas today is already used on hundreds of megaton scale. So if we could, but using fossil fuels, so if we could replace this by a sustainable route, this is really an attractive way forward. How do we do this? That was the tricky part. So the issue with making hydrogen, it's actually, and some people may disagree with me, but it's quite an easy reaction. So you need a catalyst, and we have many possibilities from platinum, but also precious metal free. And you usually do not have a selectivity problem. So you can work in 55 molar water, you make hydrogen, and it's a clean reaction. If you want to reduce carbon dioxide, ideally from air, you deal with extremely dilute sources, and also the solubility of CO2 in water is quite low. And then it's very difficult to make a selective product because you usually have a lot of co-production of hydrogen and then maybe other carbon products you're forming in this process. So what we have developed over the years is just a molecular engineering approach where we integrate catalysts on surfaces, in particular semiconducting surfaces, to make this CO2 reduction energetically easier and more selective and actually feasible. That's the most important. I will not delve into details because this would consume the full 30 minutes I have, but I just showed a concept. We usually have some molecular catalysts. This can also be biocatalysts. We introduce linkers and then surface anchor groups. And these anchor groups then we really immobilize on the semiconductor. And ideally, we also tune the microenvironment. So for example, to make sure we have good access of our substrate, CO2 and water to the catalytic site. We have actually a release possibilities of the product. And also we want to stabilize the intermediates, again, to make it as energy efficiency as possible. Because if we don't do this, we need too much photovoltage and actually our chemistry does not work. So I fast forward to the first functional system I'd like to show. So it actually took us the full 7 years to get there. And the first system we put forward here was actually a tandem system. This means we have 2 light absorbers. One is a business vanadate, wide bandgap semiconductor absorbing UV and blue light. And then this is complemented with a lead halide perovskite that absorbs the rest of the visible spectrum. So we have 2 light absorptions. And then we have sandwiched 2 catalysts. One is our syngas catalyst that I will show in a second that takes CO2 and water into our syngas, and an oxygen evolution catalyst that oxidizes water to oxygen. And here you can really see the analogy to natural photosynthesis. In natural photosynthesis, the leaf takes light, has 2 light absorptions with photosystem 1 and 2, oxidizes water to oxygen, takes CO2 and water into sugars. So the only real difference from a chemical point of view is we're not making sugars, but syngas, and we want to make syngas because it's technologically easier to use than glucose. And how does this look like? So here in the bottom is a video. This video is 100 times forward. It's not real time, but it illustrates the point. So we have here this artificial leaf in the center. Light comes from the left, and you can see some bubbles on the front. That's the syngas coming out, and in the back the oxygen. And you can really see one of the advantages of this leaf configuration, that actually the products are separate. So the syngas evolves on one side and the oxygen evolves on the other side. The scheme here on the top was of course a bit of an oversimplification. It actually requires quite some sophisticated tuning of layers to make this work, and actually selecting the right layers as well. Maybe if I start here from the back, so the light comes towards this business vanadate semiconductor. Important here is already that we have a catalyst layer. This is a cobalt layer that we just very thinly deposit on top of the bismuth-vanadate that is transparent. Otherwise, the light would not even reach the bismuth-vanadate. The bismuth-vanadate then is semi-transparent, so there's still some light coming through, and then it reaches the perovskites, the second light absorber. These perovskites are extremely moisture sensitive. So if we want to use those light absorber in aqueous solution, we really need to encapsulate them. And how do we do this? We first sandwich them between a nickel oxide, a hole transport layer, and a PCBM electron transport layer. And then we have usually some encapsulant. In this case, it's a Fields metal. That's an eutectic metal that melts at 80 degrees. So we just take the device, heat up to 80 degrees, and this eutectic metal can really seal off the perovskite. And since it's an alloy, it's conducting, so we can really connect this now to our co-catalyst. And the catalyst we are using here is a forest of carbon nanotubes with this cobalt porphyrin that is known to be an excellent CO2 reduction catalyst at low overpotential, and indeed it operates here with turnover numbers of 3,000. It's quite an effective system. Here's a little bit of data. Also here, I don't want to delve into details, but a few things should be said. This is now the leaf, but actually with a wire to make sure we can measure the photocurrent. And you see here the current density versus operational time. The gray is in the dark. The white is really when we have our solar light simulator switched on. And then after 70 hours, we switch off again. And you can see this green trace shows the photocurrent. It's very stable. And after a few days, it collapses to zero. And this is usually when our encapsulate breaks. So when our Fields metal gets a bit leaky, a bit of moisture gets into the perovskite and decomposes the perovskite, and that's the end of the device. The experts will also spot that the current density is actually quite low. So we are not overly proud of 0.13 milliamps per square centimeter, but it is a standalone device, and it was one of the very early ones, which still was important, certainly to us. But the low current density of this very first leaf also means our solar to fuel energy conversion efficiency is quite low. It's about 0.1%. So this means from the solar energy which we shine onto the device, only 0.1% is actually stored in the syngas fuel. And these traces here show effectively that we are generating carbon monoxide and hydrogen, roughly in 1-to-1 stoichiometry under these conditions, and also oxygen. The stoichiometry is not perfect because bismuth-vanadate is not entirely selective for oxygen evolution. And we have proven that CO2 is the source of our product. So isotopic labeling is always very important, and I'll come back to this a little bit later. So the second generation looks like this. This is not this thick half-centimeter devices anymore. We can engineer them now very thin. And you can see actually they're only about 1 millimeter thin, and they're even flexible. And that's really great because this allows us much less resource use and of course also flexibility for deployment. What we've done here is effectively we replaced the glass by titanium foil and by conducting plastics, and we also replaced the Fields metal that's quite heavy by a graphite epoxy encapsulant. So these are a few modifications that allowed us to make this much thinner. And this looks now like this. We have the bismuth-vanadate on the outside, the perovskite on the inside. So it's not a true tandem anymore because the titanium foil is not transparent. We can only irradiate one of the light absorbers at the same space. But still we generate syngas on the bottom here and oxygen on the top side. And how does this look like in real application? So if we put this artificial leaf here into this tank, we shine light. You can see once we start forming bubbles, it actually starts floating on top of the surface. And that's extremely interesting because this means this device is so light that we could even use it on open water sources. And this really inspired us quite a lot to go outside. And in fact, I'd also like to show you a couple of pictures from Cambridge. So this is the back of St. John's College. And if I wonder where I'm at the moment, I'm actually sitting in this building where the arrow goes. And here at the front, there is a river. And on this river, we tested this device here. You can see here this artificial leaf. We've put it into a sealed plastic bag with carbon dioxide and water. And when you shine light, indeed, it converts this carbon dioxide into syngas. So the idea is really use such systems for CO2 water conversion into a net zero carbon-based fuel, and this could also be called an artificial lotus leaf. So at this stage, it's time for me to give credit to the people who actually did the work, really the person who assembled the first standalone artificial leaves, who developed the lightweight systems as well. In particular, the lotus leaf was really all done by Virgil Andre. So he showed we can take CO2 and produce gaseous fuels, syngas, carbon monoxide, and he developed many different iterations of these systems very successfully. With this platform in place, we could now demonstrate a lot of different applications. So first, Esther Moore, I forgot the name actually to put here, is she showed we can put biological catalysts also instead of this cobalt porphyrin. And when we use, for example, an enzyme known as formate dehydrogenase, we can reduce CO2 not to produce carbon monoxide, but actually formic acid, which is also an interesting energy carrier. Motia Rahman showed that we can actually take carbon dioxide with another catalyst to ethanol and propanol. And Motia did the work that I will present at the end, and I will explain a little bit more about this multi-carbon production here. And then we also have Superjit Bhattacharjee. What he showed is we can use these devices for waste upcycling. So we can also just feed biomass PET in there to do chemistry. And most recently, IYCN has shown, not in a leaf configuration, but similar, that we can even do chemistry directly from atmospheric carbon dioxide. Leading to this work, Michaela was actually the first person in the group who demonstrated that we can really encapsulate perovskites. And this was for us quite important because perovskites, as I mentioned before, are notoriously known to be moisture sensitive, and it wasn't quite clear if this could be used at all in aqueous solution. So for us, this was a really big step forward of showing photoelectrochemistry and artificial leaves with these perovskite light absorbers. Yishan Lai, she actually developed this business vanadate titanium cobalt photoanodes that we are still using until today. And last but not least, Jan Yukoski here developed the CO2 reduction catalyst that we utilized for this floating artificial leaf. So I'm showing this to show it is really a very collaborative effort that actually took us many years. So it's not just one single system that appeared. Actually, this is a real significant effort from our team. So these floating applications are actually not entirely new to solar energy. So in fact, the photovoltaic community has been thinking about this for quite a while. And you will find in many countries installations where this has been tested actually on open water sources. There's just one example from South Korea, where these photovoltaics are shown, or these giant floating solar flowers. And all you can see here are actually silicon photovoltaics that are connected to the grid and essentially produce electricity. And there have even been people, and that's an artist impression, not reality, but there have been people already dreaming about millions of floating pods in the oceans that could be used in a future scenario to generate power and energy and probably fuels for humans. So maybe, you know, our little leaves are a first step towards such a reality. What about scaling of our system? So far I've shown 100 square centimeters, but last summer actually my team, that's Virgil and Mote, have introduced. We teamed up with Sam Stranks here from chemical engineering and Miguel and Yishuan, and we built the first large prototype reactor. So this is now a 1 square meter reactor, and this was in Italy where we could demonstrate operation over 3 days, really using real world conditions, sunlight, and the conversion of CO2 to syngas. So I'm showing this because artificial photosynthesis is not anymore an abstract or theoretical concept. Actually, there are a couple of real tangible devices from us, but also other research groups around the world. Okay, but to wrap up, I'll come to the liquid solar fuel synthesis now. So in this case now, and this is Motia Rahman's work, we have left the tandem stack and the artificial leaf more or less intact. We've only made 2 modifications. First, we introduced another whole transport layer. This one just helps us to get a little bit more photovoltage out of the device. And then we introduced a new catalyst for us here, this copper palladium catalyst, which is capable to produce ethanol and propanol. And this copper palladium catalyst is shown here with a stem EDX. You can see the copper and palladium is really in this nanostructured catalyst. And ultimately, we can really see phases and fringes from copper and copper palladium also in the high resolution TM here on the bottom right. So how does this catalyst perform? In this case here, what you can see is the Faraday efficiency to produce alcohol versus different compositions. And this is now only electrocatalysis. So we are applying a potential of minus 0.53 volts versus RHE, and just look how much of actually alcohol is being produced in this case. And we break it down in ethanol, propanol, and the total amount of alcohol. And what Motia did here is effectively just started off as copper, introduced different amounts of palladium, and looked at the optimal composition here. And this is really shown here with this copper 94 palladium 6 catalyst, where we get up to about 10% of Faradaic yield for alcohol production. Importantly, we really have to prove here that the alcohol comes from CO2, and this we can do with CO2 labeling. So we take C13 labeled CO2, purge our reactor in this case, or electrochemical cell, run the electrolysis, and then look at the solution by proton NMR spectroscopy. And in this case, we just look at the proton peaks from our alcohol. And if the alcohol comes from C13, then we should see a characteristic splitting, because now we have introduced a spin half C13 carbon. And that's exactly what you see. So these are the peaks from propanol here in orange, and in blue for the ethanol. And for the ethanol, you can immediately see that it just splits in two regions. And you have exactly the same for the propanol, and this is consistent with isotopic labeling of our product. So indeed, at least the vast majority of our product is really derived from CO2, and this was a very important demonstration here for us. Then how does the final device look like? So here on the top, you see actually the devices. On the top right here, this is the artificial leaf with no wires, but for some of the characterization, we also introduced 2 wires, so that actually we could control the current flow between the 2 electrodes, and also at the first plot to apply potential. And this is how it looks like with the wires. We have current density versus applied bias. And most importantly, when we have no bias, we see already a current density. So this indicates very strongly we have bias-free operation. And indeed, if we run the device without any extra voltage, no sacrificial chemicals, we see a constant current. And this constant current is due to CO2 reduction coupled to water oxidation. And in this bias-free device, we see this Faradaic yield of alcohol of about 7%, which is maybe not as high as we want in a final device, but it's a nice illustration that in principle, these multi-alcohols can be made. To show that we really make oxygen on the anodic side, show here on the bottom left the oxygen evolution over time. And also here at the bottom, we see also here actually the amount in micromoles per square centimeter of the alcohol. To make sure the chemistry is clean, we also calculated the charge that should pass based on the products we are producing. And indeed, it's a 1-to-1 ratio from the photoanode to the photocathode, meaning there are no side reaction, at least no significant side reaction that we haven't taken into account. Okay, I think my time is coming to an end, so I'd really like to wrap up with one summary slide. This here was our very first standalone device for water splitting to make green hydrogen. By GRU Lin in this case, you can see the 2 compartments with a membrane, but we could only make hydrogen and very actually inefficiently. 11 years fast forward, we can integrate all of this in about a millimeter thin device. We can produce them at a scale of a square meter, and the devices have become much more efficient. But I think more importantly, we have learned how to design them, and we have learned how to integrate catalysts. And this goes from solid state to molecular to biological catalysts. And this has really enabled us to convert carbon dioxide to a range of different products, including ethanol, propanol I've just shown, but also do other chemicals reactions such as waste upcycling. And what we're doing at the moment is we keep expanding the chemistry scope, but we also like to think a bit more broadly about light management in these devices. So currently, us and also most of the community are really only looking at the UV and a bit of the visible spectrum. So we are throwing away a lot of energy from maybe the red region of the visible and infrared. So what we do at the moment is see if we can integrate heat management in our systems and have something that's close to thermocatalysis coupled to our photochemistry, introduce or use heat gradients in the form of thermoelectrics to provide extra voltage to our devices, and even think about water vapor generation for water purification and other aspects that may be relevant for a clean and healthy future. And that's really it. I'd really like to thank the funding bodies. I'd really like to thank all of my group. I could unfortunately only highlight the work of a very few, but I have a really fantastic team. Also the collaborators, Richard Friend helped with the perovskites, Sam Stranks with the device assembly on a larger scale, and Dominic Wright with the catalyst preparation. And as always, always looking forward to applications from enthusiastic PhD students and postdocs. And I hope you found it interesting. I'm looking forward to the discussion.
Thank you very much, Professor Reisner, for your presentation and for sharing the progress in this very important field of photovoltaics. We are now going to move to the Q&A session of the Science Café. And the first question comes from the audience. What is the scope of these liquid solar fuels? Could they be easily adapted to the engines and devices we are used today?
So, I mean, first important comment is these technologies are certainly not commercially ready. So many communities just demonstration what's possible, and they will require a lot of optimization and development. But I'm getting more and more optimistic, since I think the momentum is building up significantly in the community. To address the question, yes, I mean, this is exactly the plan. So for example, with syngas, our motivation was, could we just take a petrochemical factory, if you like, cut away the fossil and just insert the basic building blocks from CO2? And I think that's completely possible. So I like the idea of keep the current infrastructure intact, but just cut the fossils out and replace it by some solar feedstocks. And you can certainly do, you know, if you can make at a large scale, super cheaply, hydrogen, CO, methanol, ethanol, etc., then you really have a very nice way into rebuilding a lot of the current chemical industry and make it sustainable. And of course, if you bring in waste as well, you know, you can think about lignocellulose. With lignin, you have aromatic building blocks. Cellulose gives aliphatic building blocks. So I think there are a lot of possibilities. And of course, I've shown ethanol as a product today as well. Ethanol is a great fuel. If you go to Brazil, you know, and you go to a gas station, you can in fact put in your tank from ethanol to gasoline, anything you like. They call them flexicars. And this is all possible. It's, of course, there's a bit of an activation barrier, but Brazil here would be a fine example what's possible if we push a little bit, and we can easily adapt our engines, etc., to all sorts of energy vectors.
It's good to know that we can adapt. The next question is, what happens if we cover the oceans with those photovoltaic panels, but we cover the energy that algae convert? By Byron Lopez.
By what, sorry?
It's the name of the person who made the question. Okay, Byron Lopez.
So the question is, if we cover the oceans with our devices or algae, or both?
Do you want me to repeat?
Yes, please.
What happens if we cover the oceans with those photovoltaic panels, but we cover the energy that algae convert?
I try. Okay, I'm not sure if I understand, but I'll give an answer. So I think, yes, the question is actually a very good one. First of all, we have to be very careful with any of such applications where we put it. So there are, of course, huge implications into biodiversity and the environment if we start covering square meters of oceans with any sorts of device. We need to investigate what shading does to the marine life. We need to make sure no toxic elements leak into the oceans, etc. But this being said, I think it's quite attractive at least to think about this, because the problem with solar technology is it requires a significant amount of land. It's not so much that we can't do it, but we all know land is precious, and there may be quite a lot of scenarios where it's attractive to put it floating somewhere. This could just be on waste treatment plants, a dam, close to a port where you want to produce shipping fuel. On the algae, I think algae is a very different technology that you can also consider either for biomass generation or potentially even hydrogen generation. The limitation you have with algae is usually the solar energy conversion efficiencies are quite low. So with our, also I would not say we're not there yet, but in principle, our devices can get to far higher efficiencies, probably an order of magnitude at least higher than algae systems. And we are not producing hydrogen, but as I said, we could in principle produce alcohols. So there's much more value generation from such solar devices than algae. The big advantage of algae, though, is it's of course self-replicating. It's much cheaper. So I think there are always advantages, disadvantages. We see ours as a very complementary and different technology to algae.
Are there any solar fuels that are used commercially in the world?
And I would say not commercially, but they're the first steps to use some as drop-in fuels. But they are not cost competitive. And it also depends how we define solar fuels. So there is, for example, there are quite large scale installations that are solar thermal that are in Switzerland. These will be used, to my knowledge, as drop-in fuels soon actually in aviation. This includes Swiss Air. So in fact, I've recently been on a plane from Switzerland to the UK, and I saw on the screen in the plane solar fuels as drop-ins, which was quite amazing. But these are not commercially ready. I think it is just to test them and maybe to promote the idea of solar fuels. But you know, at least it's coming. It's moving into the public. There will be awareness. And ultimately, of any of these technologies, to really bring them to market, it will require massive investment. So I think it's a good step. At least we can attract some interest and then hope to accelerate the development.
The next question, are solar fuels feasible in countries that don't experience as much sunlight, or there are ways to account for that? What are the ways to get more sunshine on a cloudy day?
Yeah, I can't move the clouds away. That's a tough one. So yes, so certainly, of course, there are geographical areas where solar fuels make more sense than others. It's of course particularly attractive to if you're not too far from the equator, and arguably UK is also not the perfect country for solar fuels. But this being said, it's very similar to photovoltaics. And if you really look at performance of photovoltaics in, let's say, southern Spain and the UK, the difference is not so vast. I think you have a difference of 30–40%. So I would say, yes, of course you want to start, and it's better, makes more sense at very sun-rich regions, but this does not hold you back to use them also in other countries. So I think, long story short, yes, you want to preferentially put them where the sun is, but also, especially these leaves I've shown today, actually they operate quite well under low light intensity as well.
And on the contrary, what do you think about the African Sahara Desert countries?
I think it's very, very effective. The issues, of course, in the desert is always more a practical one. How do you deal with dust, etc., and sand? But yes, I mean, we find the idea of putting these technologies actually specifically in sun-rich developing countries is very attractive, because it's also in developing countries, there's much less of an established infrastructure you have to compete with. So here in the developed world, everything is very centralized, highly optimized, energy is very cheap, and the whole infrastructure is in place. In a developing country, very often this is not the case. So actually, our technologies are quite good on a small scale and off-grid. And we actually think that developing countries would be a very attractive starting point for these technologies.
Next question. What is currently the greatest barrier to implementing solar fuels right now?
What is the greatest what?
The greatest barrier.
A barrier?
Yeah.
I think it is really well, again, it depends on the definition of solar fuels. But if you define solar fuels of coupling photovoltaics to electrolysis, then in fact there's not a massive technological barrier. I think it is really just a willingness and investment to do it. If you define it more as really integrated devices, then I guess it's really a focus to tackle the challenges of stability, efficiency, and product selectivity to move it forward. So ultimately, it's a question of investment.
There are many more. Sorry?
Yeah, just from an academic point of view, it's just very difficult with an academic laboratory alone to bring these things on market. So ultimately, it needs partnership with companies, governments, etc., to build large initiatives. And then I think this is very possible.
We have another question from the audience. Thank you, Professor, for your great talk. My question, the artificial leaf is highly integrated, but whether the mass transfer between cathode and anode will be an issue. Thanks.
Yep. No, thanks for that question. I mean, this is one of the challenges. So I've shown in the introduction two configurations. The layered configuration has, I have to admit, I only pointed out the advantage and not the disadvantage. So the advantage is you have nice product separation that I mentioned. On the other hand, you effectively, indeed, you have mass transport limitations because you produce at least, or you release protons on one side and consume it on the other side. So you build up pH gradients. But this can be addressed with adequate buffers or pHs, or even make sure you do not build up too long distances between your cathodic and anodic part. So, you don't need to have a square kilometer single sheet where the protons have to travel around. I think this can be engineered. But this specific problem is completely solved in the second configuration that I did not discuss today, where you have the light absorbers side by side. So in this case, you do not build up pH gradients, but you have not a disadvantage that you produce all products at the same site. So you have hydrogen, CO, oxygen all together, which is an explosive mixture. So then you need a membrane to separate them. So, that's unfortunately not the perfect solution, but we do have different configurations to solve and address all of these limitations.
Another question. Here is Luis Amesquita, Guatemala, delegate from IYCN. How the solar artificial leaves are made? Are they printed?
Oh, that's a good question. We would love to do this, but we usually emphasize very simple fabrication methods. And I guess that's because we are a chemistry laboratory. So most of the layers have shown us spin coated or just deposited. So the electrocatalyst would be electrodeposited, but then the light absorbers, the charge transfer layers, either the electrodeposited or spin coated. So we usually, there's one evaporator step, but generally speaking, it's fairly simple, readily available deposition techniques.
In your presentation, you showed very beautiful devices that float on water, but if I understood correctly, they were covered by a plastic foil. How would you extract the fuels from in this kind of devices?
Yeah. So in this case, we have them in the plastic bag because we need to entrap the carbon dioxide. So in this particular device, we start with concentrated CO2, and then we convert it into our product. So in this system, yes, we would extract it with a syringe. Of course, in a dream reaction, you would just source the CO2 from air, but you still have to capture your product. But this could ultimately just be in a tank, right? If you make a liquid fuel, and let's say you don't make ethanol, but you go to butanol or hexanol, those alcohols phase separate from water, and then you have quite an easy way, I think, to separate and collect the product.
Okay. So, Professor Reisner, thank you very much for sharing your research work and your knowledge with us, and of course for answering all of these interesting questions. I will now pass the word to my colleague Tracy, who will introduce our organization. So
thanks for having me.
Thank you very much again.
Thank you.
Thank you so much to Professor Reisner for his presentation, as well as for giving us a wonderful explanation on liquid solar fuels. It was very insightful and very, very educational. Thank you so much. I'd like to talk about the IYCN Science Café series. This is the second of our of the IUPAC Top 10 Emerging Technologies in Chemistry for 2022. Our first one was in May 2023 and will be uploaded soon to the YouTube channel. Please follow us under the IYCN channel for YouTube to see when this video will be uploaded for demand later. Thank you. The IYCN has a commitment to equity, diversity, and inclusion, A network such as IYCN can only succeed if early career chemists from all nations have the opportunity to join, network, and participate. A platform like IYCN is a constructive route of bridging international borders. To keep up to date with us, please follow us on www.iycnglobal.com. Thank you again to the speaker and to all the audience for attending. Please follow us on all social media or visit our website for upcoming events. Have a good whatever time it is. Thank you again, Professor Reisner, and thank you to my colleagues, Walid and Elisa.